So, what constitutes value? Well, let's take a look at how economies made this use of value in ancient times, right? Well, we had people who would say that value is equivalent to human time, right? Time is time was the value system. So let's say you were a farmer and then you produce crop, right? You might spend some X amount of hours, and these X amount of hours would equal Y amount of like food, right? Let's say this is a farmer and you need food to survive, right? You also might need something like, um, for example, protection, right? Protection. And you could have someone else, there's X1 and Y1, right? And you could have someone else who was a soldier who would spend some amount of hours in protection, right? And the value in the system was determined by the amount of hours that a human spent, along with some level of risk and some level of sort of like ease or difficulty associated with the task, right? So this farmer could pay, right? This farmer could pay the soldier, um, could pay the soldier with time, right? With the equivalent amount of time that they spent to create the food, right? And the soldier would equivalently pay back the farmer with some amount of service hours, right? And this is how the economy worked in most of history, right? You would have people who exchange essentially effort or human time, and this would be the source of value. So now let's take a look at what happens when you introduce a monetary system. Now, one of the earliest examples of this was people would trade rare items, right? People would trade items such as maybe like shells, right? You would have rare shells, or you would have items such as maybe even like human bones, right? Because those things were rare, right? And one of the key items in this trading system was gold. And the common denominator behind all of these items was that these items are rare. These items are rare. Now, what does rarity have to do with it? Well, if we take, for example, potatoes, right? If we had potatoes and these were a source of food, right? Potatoes have some sort of intrinsic value to them because it took some amount of human effort to grow that potato, right? And you need potatoes to survive. They're a source of food. But what about all of these rare items? Well, these rare items have value because they are rare, because it's difficult to find, right? Maybe like these shells and bones and this gold, especially gold, they're very rare to find, which means that you can't produce these items out of thin air, right? It's very difficult to actually accumulate these items. So gold became a standard for the global currency because everywhere in the world, it was very difficult to find gold, right? It was very difficult to add gold into the system. Now, this meant that gold had some sort of monetary value that could be traded. And this is important because a potato, right? A potato will spoil, right? A potato, most food sources, right? Potatoes, an apple, rice, right? These are things that will spoil. Gold will not, and it's easy to trade, right? It's very easy to trade something physical that has value attached to it. So this is where value comes from, right? Gold has value because it is rare. Now you can start getting deeper or closer to the present with this and start talking about paper currency and banks. Now the difference is with paper currency, this has value because we have deemed it has value, right? A $1 bill, in terms of the actual paper used, may not actually be worth a dollar. It may be worth less or more with the actual materials it's used, right? I, I mean, in history, you would see things like nickels, which were melted because their nickel content was actually worth more than nickel itself. But nowadays, usually paper currency, well, maybe not in our current financial system, but usually these types of currency have value because we have deemed it has value, $1 of value, right? And banks became important because they were a way for people to agree on how to share this currency, right? Banks became important. Right? Banks became important. And banks provided some sort of security, right? You could place your money in a bank and you were reasonably confident that your money would stay there. And it would be much easier to store this money inside of this bank than to keep it around in your pockets at all times, right? So this was essentially a high-level overview of why things like money and banks came into play, because it's much easier to carry this around in your pocket than some rare items, right? You would see in like England, right? People used to barter with items that were made of gold, that were made of rare metals like maybe copper or silver, right? But the problem with this is that it was difficult to make transactions, right? If I wanted to pay you for some amount of food or for some service or something, I would need to physically bring these items to you. So paper currency became an easy way to have a common denomination for money that people could exchange, right? Banknotes. These were just slips of paper that are evidence of an agreement, a payment. So this became a key aspect or a key player in our economy, this idea of paper currency. So with that kind of rant out of the way, let's get into cryptocurrency, right? So why does cryptocurrency have value? Well, cryptocurrency, it doesn't have value because we deem it has value. Instead, cryptocurrency dates back to this older form of value where crypto has value because it is rare. And this rarity is the foundation for all cryptocurrency. So now we know what value is. If I can clear this. All right, so now we know what value is. We're going to take a complete 180 pivot. I'm going to drink of water. We're going to take a complete 180 pivot, and now let's talk about encryption and hashing, right? So cryptography. Right, cryptography. So what is cryptography? Well, it is some way, in its essence, it is some way to verify trust, right? Um, how do we how do we use math to guarantee trust in a system? Well, there are two key terms here that most people get confused, right? There is something called hashing, and there is something called encryption. Now, how I like to think about these two is that hashing is a one-way door, whereas encryption is two-way, right? So hashing is one way, whereas encryption is two. How does that work? Hashing, you start with some x, right? And you have some mathematical function, right, that transforms x into y. Encryption, you also start with some x, so this is hashing, right? Encryption, you also start with some x and turn it into some y with some encryption function. However, with encryption, you also have the two-way street, right? It's a two-way street. You have decryption to go alongside with it. So encryption allows you to turn some x into some y, right? Usually with some given key, right? And you can turn y back into x with some sort of key. And k1 could equal k2, or it couldn't, right? Uh, so you can see there's some encryption functions that use the same key. There's some that use different keys, right? Um, hashing. Hashing, it's a one-way street. These are difficult functions to crack. It is very difficult to take a hash function. It is very difficult to take a hash function. Oh, there we go. A hash function, right? If we have x and we apply some f onto it, some hash function f onto it, it is implied that we cannot go back. This is impossible. It is not impossible, it is just improbable. All right, so let's talk about one of the most common hashing functions. In fact, Bitcoin uses this function. You may have heard of it. It's called SHA-256. Right? Now, SHA-256 takes any string. Now, if you're not too familiar with computing, a string is just text, right? It takes some amount of text, like, let me actually start coloring some stuff here. It takes some amount of text, say like, hello, right? And this function, the SHA-256 function, takes that text and applies a transformation onto it. This transformation converts it into some string of bits, right? Zeros and ones. Right. Now, how many bits? Well, it's 256 bits, right? So 256 bits of zeros and ones. Essentially a string of 256 either zeros or ones, right? Now, if you think about this, right, if you've taken any sort of introductory statistics course, we can calculate how many possible combinations there are, right? So given a SHA-256 hash, right, we took a string, and then we went down this hash function, and it converted it into this array of bits, right? What does this mean? Well, in our universe, there are 10 to the 80 atoms, right? There are 10 to the 80 atoms. Now, if we take a quick look here, right? Let's do a quick calculation. Let's take 2 to the 256, right? This is about, what is that? 1 times 10 to the 77, right? 1 times 10 to the 77. This SHA-256 hash has around 10 to the 77 cases. You would need about 1,000 atoms per case in the entire observable universe to even think about mapping this hash function back onto itself, of checking every single probability, not to mention the amount of time it would take, right? If you just took 10 to the 77 amount of milliseconds, right? Let's take a look at that. So 2 to the 256, let's say it takes a millisecond to check every case, and we convert that to seconds, right? Or let's convert that to years. Right. That that is a lot of years, and you're not gonna be able to crack this code, right? So, what does this say? Well, it tells us that a hash function basically guarantees security. Now, why is that? Well, because this is a one-way function. We didn't define a function that goes backwards. Now, you can go into sort of the mathematics of this, whether or not it is possible to define such a function. But as of today, right, it is within our reasonable assumption that we're not going to be able to find a function. We're not going to be able to find this function, right? So if you think about like reversibility of functions, right? You have some f, and you have some inverse of f, like f prime, right? That's a terrible f, like f prime. We are fairly certain or fairly confident that you're not going to be able to find an f prime for SHA-256, which means that the only way to check if a hash is correct is if you had the original x, right? If you had the original x. So a hash function, again, just to recap, it's a one-way function. And let me actually give you an example in case this isn't making too much sense. A hash function, a simple one, could be the prime number, the prime factorization of a number, right? What does this mean? Well, prime factorization of a number. Let me give you the number, let's say 74, right? Now, you could start factoring out this number, right? Let's take 2 out of here, and then we get a 37 if I'm correct, right? And that's a quick prime factorization. Let me actually pick a better number. Let's pick like 96, right? 96, let's factor out 96. Let's take a 2 out of here. It's going to be 48. Let's take another 2 out. It's going to be 24. Take another 2 out. That's going to be 12. Take another 2 out. That's going to be 6. 2, and then 3, right? So 96 would be 2 to the 5th times 3 to the 1st, right? Now, as you'll notice, this is quite a tedious process. Imagine if I had a huge number, right? A huge number, like let's say somewhere in like the millions, right? And I told you to give me the prime factorization of this number. This becomes an incredibly tedious task to do. However, are we able to verify this, right? How does the verification process sound? Well, if I gave you this, right, you could very easily check if I was telling the truth or if I was lying or not. Let's take a look here. 2 to the 5th is 32, right? And then we multiply by 3, that's 96. I just verified your work with very little effort, right? If you gave me the prime factorization of a number in the millions, I could very quickly multiply the numbers together and check if it matched the original number, right? I could do the work myself to see if you put in the work. However, here is the key. Here is the crux of the hash function, right? A hash function, no, a hash function implies work. That is the crux of hashing, right? It implies work. Many times, this work is evidenced by time, right? Now, why is this, right? Let's say I told you that I had some x, right? And we put it through SHA-256, and we came out with some y. And I wanted you to tell me what, I gave you y, and I wanted you to tell me what x was, right? How would you do that? How would you accomplish this task? Well, as I told you before, we're fairly confident that you don't have a reverse function. So let's assume that one doesn't exist, or it's very hard to find, right? The only way you would be able to tell me what my x was is if you tried every x. Now, this is crazy, right? Because you have no way of reversing this. So instead, what people have found is that you can prove work by trying out every x, right? Let's say I told you my x was in the range of 0 to 100, right? In the range of 0 to 100. Now, what this means is that if you were to tell me the x, I'm fairly certain that the only way you found out was because you tried every x, right? You tried putting in 0, and that resulted in some value. You tried 1, that resulted in some value. And at some point, maybe you went to the number like 49, right? And check, that 49 produced the same output as y, right? So you can tell me, okay, I know your x was 49, and I can be sure you've made the work. Why? Because the only way you knew that x was 49 is because you tried every possible scenario, right? You tried every x. So hashing implies work. Now, if you recall, we said that earlier that time was a sort of value, right? It was value in economics. And this is why time is value as well in cryptocurrency, right? This is why time is such a crucial aspect of cryptocurrency. So now we know, or hopefully we know what value is, right? And now we know what cryptography is. Now let's take a dive into actually the crux of cryptocurrency, right? So the incentive behind cryptocurrency, the incentive is that we have some system that allows people to have mutual trust. We have to have some level of trust in the system, but we also want to have some sort of decentralization. Decentralization. What do I mean by trust and decentralization? Well, normally in our current economy, you would probably have your trust in some sort of central bank, right? This goes back to our idea of the bank. The bank has authority, and you trust the bank that the bank will honor their side of the deal, and the bank offers trust back to you, right? Now, what does this trust imply? What it implies is that if I tell the bank, right, if I take some money out of the bank and I write a check, right, I could write a check um, that says like, Alice paid Bob, Alice pays Bob, $50, right? I have trust in the bank that the bank will manage this transaction and transfer the funds accordingly, right? This is where the trust comes in. However, the bank is not decentralized. It is a central authority. Now, imagine if there are some problems with this. Now, cryptocurrency deals with some of these problems, and so for example, if I wanted to transfer funds overseas, right? If I wanted to send funds to someone in France or someone in England, right? I would need to contact their authority, right? I would need to somehow transfer this information over to their authority that I wanted to pay someone overseas. Now, this may take time and may be tedious, and this is still some sort of central authority governing the entire situation. But here's the crucial thing. A bank, we have pretty good trust in a bank, right? The bank guarantees trust. But without some sort of central authority, how do we trust others? How do you trust others if there's no judge, right? If there's no referee in the game? Imagine like you're playing soccer, right? You're playing soccer, there's a referee in the game who ultimately gets to make the calls. What if someone's violating the rules, but there is no referee, right? How do you guarantee that everyone is playing on a even playing field? Well, this is where the idea of work comes back. Let's imagine this situation, right? We have a community ledger. What do I mean by a community ledger? Just a simple sheet of paper, right? Simple sheet of paper. And then now let's say that we have some number of people, right? We have Alice, right? And let's say Alice pays Bob $10, right? And then maybe Bob pays Charles $5, right? And then Charles pays Alice $50. All right. So this is a ledger, and this is a decentralized system, right? If we post up this ledger onto a wall, right? If we just put it into the wall of like, imagine these are college students and they just have it on the wall of their dorm room, right? Well, this is a decentralized space, right? No one is governing the ledger. Everyone can add transactions as they wish. Now, maybe between college students, there's some amount of trust, right? There's some amount of trust that at the end of the month, right? Let's say at the end of the month, we all pull our funds together and we sort out who gets how much money, right? So there's some amount of trust because Alice trusts Bob, Bob trusts Charles, and Charles trusts Alice. But now, let's say Bob has some bad intentions, right? Bob wants to steal some money. Well, what can Bob do? Bob can say at the bottom of this ledger, Charles pays Bob. Charles pays Bob $100. But Charles never agreed to this, right? So there's sort of two ways of fooling the system, right? There's one way. Well, let's say Charles is a bad guy right now, right? Charles is the attacker. Charles is the attacker right here. And then Charles wants to scam Bob, right? There's two ways of doing it. One is he just straight up writes, Bob pays Charles like $100, right? Now, what if Charles had really good handwriting and can and Charles can mimic Bob's handwriting, right? Now, Charles may be able to convince Alice and the rest of the kids in the dormitory that Bob now owes him money. and then Bob would have to pay up, or maybe Bob just forgot, and then now he has all of this pressure onto him, right? So he could convince people that Bob owes him money, and then that's one way that Charles could scam Bob. What's another way? Well, maybe like they go out to eat dinner, right? And then Charles says, okay, I'll cover all of this for us. And oh no, sorry. Let's say Bob pays for the food, right? Let's say they go out, they eat dinner. The food costs $50, and then Bob covers it. And then Bob's like, all right, Charles, you just gotta pay me your $25, right? Well, how Charles could scam Bob is if Charles said, Charles pays Bob $25, right? But he only writes this in such a way that Bob can only see it, right? Let's say he writes this down in the ledger, right? But before the end of the month, he goes back and erases it somehow, right? He like sort of fudges the numbers a little bit, lies to Bob, and then Charles made Bob believe that he paid him $25. However, he didn't actually pay the money, and nobody else knew about this, right? So these are the two scenarios, right? Where where Bob pays Charles unwillingly, or when Charles misleads Bob into paying him money, right? There we go. So, bit of a tangent there, but I assure you it's all important. We have this ledger. This ledger guarantees decentralization, however, it does not guarantee trust. We're lacking trust, right? We're lacking trust. So, I want you to take a moment and just think about how can we add trust into the system, perhaps with some of the cryptography we've been talking about earlier. Now, let's imagine this, right? Let's imagine that we had a lot of computers that hosted this ledger, right? That this ledger was run on a computer network. Now, each person has their own computer, what we're going to call nodes, where each node is just a computer, right? If we have some amount of nodes, and we start telling these nodes about transactions that are performed, right? So let's say between Alice and Bob, there's a transaction for like $10, and then between like Bob and Charles, right? You can think about just writing these down on the ledger, right? Now, let's say that this ledger has some amount of lines we're going to add into it, right? I forgot the number for Bitcoin, but I think it's somewhere maybe like 10,000 transactions. It might actually be less than that. But let's assume that Bitcoin runs off this idea that each ledger contains 10,000 transactions, right? Now, how do we verify, how do we guarantee trust in this ledger? Well, we do what's called mining, right? Mining this block. So what happens is we can easily turn this ledger into text, right? It's already text. Let's just assume that this is the text we're gonna put into our hash function, right? Now what we're gonna say is, we took this text right here. Let's call this maybe T for text. All right, this is a text that's already on the ledger. What I'm gonna say is that I'm gonna try to find a number where T goes to SHA-256, and this T, after going through the SHA-256, has some amount of leading zeros. Right, some amount of leading zeros. Let's say 50 leading zeros. Now, what does this imply? Right, what does this imply? Wait, sorry. We're gonna add some number to this T, right? We're gonna add some text in front. Let's call it some S, right, in front of this T. So we're gonna take this T, we're going to add some S in front of it, and then we're going to run it through the SHA-256 algorithm. Now, because this algorithm pretty much maps onto every 256-bit number, there are some numbers that are going to start with more zeros than others, right? There are some numbers, just by pure chance, that may start with 50 zeros. It's highly unlikely, but there's some chance, right? Now, if we modify this S, right, we get to modify this S. If we modify this S, well, we can say that, okay, let's change this S until we find a number, just by pure coincidence, that happens to start with 50 zeros. We all agree on that, right? Well, this takes work. This takes work, right? This is what people say when cryptocurrency has work inside of it, when people are asked to prove their work in crypto. The work is the varying of S that until you find a number, until you find a hash that has 50 leading zeros. That's where the work comes in. And this work cannot be made up. You cannot make up this work. Why? Because it is impossible to reverse this function. Think about how you would have fake work, right? Fake work is impossible. You would have to find some S that works. And the only way to find it, or the fastest way to find it in our current state of computing, is just to run through all the combinations, right? Is just to run through all the combinations. Well, once we have this work here, right, we now know, oh, okay, this person has put in work. This person has tested through thousands, millions, billions of possibilities for S until they landed across a number that has 50 leading zeros. What this person now does is that this person signs off this ledger with S, right? This person says S goes on the bottom of this ledger and then broadcasts this ledger to all the nodes in the network. Let me get some more water. So this person puts S on the bottom of the ledger and then sends it off to all the nodes in the network. Now, what this node can do, this is why it's called mining, right? Everyone has agreed, right? This is part of the system. Everyone agrees that, okay, nice work. You put in the work, you put in the effort, and you found this S, right? I will award you, or the general community will award you, by saying S receives, let's say, $1 out of thin air, right? And this is just because we deem that the cryptocurrency has this amount of value. We can just say that S, okay, he just pulled $1 out of thin air. This is how money enters the system. This is how cryptocurrency, how money, how all the Bitcoin that exists on the network right now, this is how all of it has entered the system so far. Because this is like a miner, right? Like a miner who has just found a bit of gold, right? A miner who has just found some amount of gold, right? This miner found this gold, and now he's bringing it into the community, right? He's saying, wow, I found this amount of gold worth $1, which is probably a lot less than what gold is worth, right? He found gold that is worth $1, and he's saying this is into a now global supply of gold, right? This miner has just made money mining this gold. Now, how do you verify trust, right? Because we're all about the trust in the system. We already verified decentralization. Now we need to know if there's trust in the system. Well, all of the computers could just see if that person was actually correct. See if that person was correct. They have the ledger, they have the T, they have the S, and they have the SHA-256 function, right? And they could very easily check, okay, let's plug this into the SHA-256 function, and then we're going to see if our result has 50 leading zeros, right? We'll see if our result has 50 leading zeros. If it doesn't, well, it means that that person was lying and they didn't put in the work. But if it does, that means, okay, that person put in the work, they found the S, now this is a verified block in the blockchain. Hold up there. We said that there is a blockchain, right? This is a blockchain. Why is it just not like blocks, right? It is a blockchain because this hash from the previous block is the first line on the ledger, right? So the previous block, right? If we imagine there's a block right here, and we have some hash, this hash becomes the first line in the new block, right? And then now we have T, and then now we have S, right? So it's really like, imagine if we had, this order doesn't actually really matter. So imagine we have like hash, and we have T, and we have S, and then we run it through SHA-256, and we get some result, right? So now we know that this was part of the chain, right? It's a chain because this block was the first block that went into this, right? And then if we imagine the blockchain, right? It's a blockchain. It's a link of blocks, each with their own hash being the first line in every new ledger. And then now it means that this blockchain goes back all the way to the very first transaction ever made, right? Now, if you kind of think about this, right? How did money even enter the system? It was because people mined it. Just like how people discovered gold, right? They had to find the gold by mining the gold from out of the earth, right? This is where the mining comes from. There was 0 Bitcoin in the system originally, right? There was 0 Bitcoin. But the very first person who found the first ledger put in the initial amount of Bitcoin. I think it was 50 in the initial iteration, right? And then throughout the years, to prevent this Bitcoin from exploding, it's been like I think every couple of years this thing gets halved. So miners in a few years might be making 25 Bitcoin, then 12.5 Bitcoin, and then it keeps on going on, right? So there will only be some max amount of Bitcoin that's ever in the system, right? This Bitcoin meter will eventually fill up, right? Miners will mine every last block of Bitcoin. They'll eventually get to the top, or very close to the top, right? Um, and then yeah, so money entered the system because uh, because people mined it out of thin air, right? They had to do the work to actually get this Bitcoin. So, all right, I kind of showed you what the basics of Bitcoin, and let's go into a bit of the details, right? Now, I mentioned before there are 2 ways that Bob could have scammed Charles, right? There are 2 ways. So this is where the trust comes in. This is where the trust comes in. We can verify trust if there's no way for people to fool with the system, right? If there's no way for people to like make money out of thin air or scam people, this is where the trust in the system comes in. So let's say our 2 scenarios. Let's cover the first basic scenario where Bob is trying to impersonate Charles, right? So Bob writes this line that Charles pays Bob $100, right? But Charles never agreed. Charles never agreed to this part of the deal. However, Bob just faked his signature or whatever. Well, let's take a look at what a transaction actually is, right? A transaction includes like the actual text in the transaction, right? So Charles to Bob for $100, but it also includes some sort of like verification, right? Or a signature. Similar to how you would like endorse a check with a signature line, right? The signature comes from Charles. Charles has agreed with his own signature that he has paid Bob $100. Now, how do we know that Bob can't forge this signature? Well, this is where sort of some of the details come in. Charles has 2 keys. Key 1 and key 2. It might actually be easier if I write this in another way. He has a private key and he has a public key. What this does is, if we go back to encryption, right? We already talked about hashing. But how does encryption play a role into this? Well, imagine that Charles has some private key, right? Um, he can sign this text, right? He can somehow sign this text with something, right? Let's say he adds some random number into the text, right? He adds a random number R, and then he says R, and then he adds onto it, he appends onto it this text, so C to B, 100, right? And he uses a hash function, right? He uses a hash function with his private key to produce some Y, right? Now, what can the public do, right? How can you verify that this is Charles's authentic signature? Well, this public key is actually sort of a way to get back, right? To go from Y back to X, right? You can take this public key and you can go kpublic, and you can find whether or not Charles is telling the truth, or if it's the real Charles. Because if Charles actually approved it with his own private key, then you should be able to take the public key and go back and then be able to see this transaction along with some random number. Now, why we add a random number in here is because, well, if Charles makes the same transaction twice, we don't want people to be able to forge his signature by just reusing the same exact Y, right? So you can take the public key and you can essentially you can decrypt it, you can decrypt Y, and you can discover if the original looks like how you assumed it would look. If it's a bunch of random noise, well then you know that Charles has been lying, or someone has trying to impersonate Charles, right? So with every transaction, there is a signature, where the signature is made off a private and public key. So what you would do is you would only know the private key yourself. You're the only one who can use the private key to sign this block, or to sign this transaction. But everyone in the world can know your public key. That allows everyone in the world to check if your transactions are valid, right? So we have a private key, we have a public key. Nice. This guarantees us trust against Bob scamming Charles by impersonation, right? That's half of our trust done. Now, the next part of the trust is slightly more difficult, right? And this is where it all comes together. This is where Bob tries to fool Charles by convincing him that he paid $25, right? And this is where the nodes come in. This is where the nodes come in. We have a whole bunch of nodes, right? Think of all these circles as computers, right? These nodes are all managing the same Bitcoin blockchain, right? So all of these nodes, some might be trying to calculate hashes, some might be mining, some might just be in the chain just to know what's going on, right? Just to be able to use it. So we have this whole blockchain, right? Now let's say Bob wants to convince Charles of this, right? What Bob might do is he might say, okay, I have this ledger here, and I write this transaction in here. I write this transaction in here, but I don't want anyone else to know, right? If I told no one else, then I have there's nothing against me, right? Well, what I'd have to do is I'd have to find the hash to this ledger. I'd have to find the S to this ledger before anyone else in the system does, right? Because we have to beat everyone else, right? We have to get this ledger to Charles. Before anyone else in the system. Now, imagine if there's like, I don't know, like thousands of computers in this network, right? Because a bunch of people in the world use Bitcoin. If there's a bunch of people in this network, then you would have to beat every single computer to finding that S, just to be able to convince Charles that you had the right one, right? Just to be able to convince Charles that you had the right ledger. Now, what next? We have this network of computers that are all racing to compete to mine the next block, right? Because it's all probability, it's all random chance. So now let's think. Imagine that Bob wins the lottery, He essentially wins the lottery and beats everyone else in the network, and he successfully finds this S before anyone else does. Okay, now we've done it, right? We've fooled Charles. We've told him that this is a ledger in which I paid you this, but I didn't broadcast to any other nodes in the network. I didn't tell anyone else, right? I kept it a secret. I told Charles something that no one else knows about. Great, I'm free now. Hold up. There's one last rule in the blockchain. There is one last rule, which is that computers will always use the longest chain. What do I mean by that? Well, let's assume we have hold on. Let's say we have two different chains here. All right, we have chain A. Actually, no. This is a better way to phrase it. Let's say we have this chain here, and due to time constraints and stuff, right, this chain splits into two. This is actually very bad drawing. This chain splits into two, right? These two computers both have a valid hash to them, right? They both found valid S's, right? So how do we know which one is right, right? This ledger, L1 might not equal L2. So how do we know who's telling the truth? Well, we don't. So what we do is we always follow the longest chain. Let's say this one grows, right? This grows into a longer chain. Okay, so now what happens is we just say, within reasonable pause, or within reasonable probability, this L2 ledger we're just going to discard it. It might have been right, but with the rules of the game, we're always going to follow the longest chain. So here's the crucial thing. Computers demonstrate their trust in a chain by continuing to mine in that chain. What do I mean by that? Well, if you're a computer, right? If you're a computer and you have these two ledgers, you can choose to trust in this one by continuing on the chain, right? Because if you continue on that chain, all other computers in the network, all other nodes, are going to believe the longer chain. They're going to believe the longer chain. So here's how this guarantees trust. Let's go back to our previous scenario, right? We have this chain, and then Bob convinced Charles that this one is the right one, right? He convinced Charles. But he didn't tell anyone else. He didn't tell anyone else. So the rest of the computers in the network are eventually going to find another ledger that works in this chain, and they're going to continue growing this chain out. So what Bob now needs to do, if you're Bob, the only way to maintain this lie, is if you're able to compete with everyone else in the world to infinity, right? If you're able to compete with everyone else. Now, usually how this works is by like the 6th or 7th block, people are like, all right, it's probably unlikely that someone won the lottery 7 times in a row, right? That's very unlikely. So, basically after a chain of like 6 or 7 that diverges, you would just assume that the new one is the correct one. But what Bob has to do is Bob now has to win 6 to 7 lotteries in a row just to be able to convince Charles that he won this thing, right? And that is astronomically unlikely, and these numbers have been picked such that it's impossible. Like statistically, it is the same as saying it's impossible, right? So by having this rule that says always follow the longest chain, we have now prevented against this sort of secret lie, right? Where you tell some node in the chain something, whereas everyone else follows a different path. So now we have proven trust, right? We have proven trust using the tools of encryption and hashing, right? Now you can end off the video here. Thanks for watching. If you stuck around to this point, I'm going to go on a little bit further just to explain some more stuff because I think this is very interesting. But essentially what we've learned so far is that we have value in a system of economics. We have cryptography. which is basically math to the math applied to computers, right? Math applied to such a point where we can guarantee trust in a system, right? Cryptography implies trust. And then now we have we now explain cryptocurrency, right? Which is a system that includes both trust and decentralization, right? Now we have created a system that's trust and decentralization. Now, as a final thing, as a final little segment here, I'm going to talk about incentives, right? Incentives. And we have sort of these two incentives, right? Why would people want to use cryptocurrency? Well, there's the people who want to use cryptocurrency because it makes transactions easier, right? When we have this decentralized system, again, if I was to make an overseas transaction, or people who don't have access to banks, right? Imagine you're in some isolated location where you don't have easy access to a bank. Well, this decentralized nature of the blockchain means that you can make transactions from anywhere, right? So this has an incentive to the general public, or the consumers, the users of this blockchain, because of the decentralized system. It also has incentive to the miners, right? It has incentives to the miners because they can earn money by mining blocks, right? By mining the gold and producing it out of thin air. As I said before, the first block contained 50 Bitcoin. That's crazy, right? The first block contained 50 Bitcoin, and then with every new block after that, new currency is added to the system. So miners are always going to get some kind of kickback, right? Some money out of thin air that they pull out, and this adds money into the system. But as I said before, to cap the amount of Bitcoin that's available in the world, this number goes down after time. So how else would miners make money? Well, here's where the incentive comes in, because people using this system may start choosing to pay miners to include their transaction in the ledger. So let's say right, this ledger has 10,000 lines, right? That means only a certain amount of transactions are going to be able to be written on this ledger. So this miner might be able to say, okay, I'm only going to include your transaction if you give me a $1 kickback, right? Now, if people are sending me like tens of thousands of dollars, right, a $1 kickback isn't too bad, right? But the user of the system is now agreeing to pay the miner $1 to use their services, right? To be able to add this transaction into the blockchain, right? So now people can start competing, right? Imagine like if this is like any other economic system, right? People are competing for the service of the miners, right? Yeah. So now we have just a quick little discussion about the incentives between the users of the system and the miners in the system, right? And yeah, that's just a brief rant about cryptocurrency. Um, and I think this is just very interesting stuff. So as always, thanks for watching, guys.